Hello students, welcome to this lecture. In last few lectures we have been discussing perturbation theory and its applications to various systems. In today's lecture we will look at perturbation theory but its application to degenerate systems, degenerate states. When we looked at the perturbation theory, we had this energy expression. Similarly, we also had wave function expression, but let us consider the energy expression. A state for nth energy level, the energy of the nth state is given by the zeroth order energy, that means before considering the perturbation, plus its first order correction plus the second order correction. Now, when you look at the first order correction, you saw that if the state of my interest is state n, I only have to evaluate this integral where it is essentially evaluating the expectation value of h prime or the perturbation at the unperturbed state. But when I look at the second order energy correction, I see that if my state of interest is n, the contribution to the correction of this nth state is coming from different values of m. What are m? M, or in this case I m, is one of the eigenfunctions of the unperturbed system. Unperturbed Hamiltonian is a Hermitian operator, so it has got a complete set of eigenfunctions. So therefore, in principle I have many integrals to evaluate when I am looking for the second order energy correction to the state n. Now, similar expression also appears when I look at the first order wave function correction. One thing is that it is difficult to obtain for the contributions from all the terms, but we discussed how we can overcome that difficulty. The other difficulty that we would like to see here is that suppose it so appears that the state of our interest En happens to be degenerate with another state or a few other states. If it is it can be twofold degenerate, threefold degenerate, or so on. In that case, suppose my state of interest is n, this one, I know how to obtain the correction from the other states which are not having same energy. But how would I get the correction from those states which are degenerate, having exactly same energy? In that case, you would see En minus Em would become 0 and then the contribution would simply diverge. Now, in that case, my perturbation theory expression that I have obtained would not be of use. This is not only this difficulty in obtaining the correction, there is another fundamental problem that has if we try to use the perturbation theory that we developed so far for degenerate states. But to do that, to point that out, let us go ahead with our discussion. Suppose I have this system, I have a system where there are d number of states which are degenerate. So I have d-fold degeneracy. In that case, in the unperturbed Hamiltonian S0, I have d number of psi n0, the unperturbed eigenfunctions for which the energy En is just equal. So E10 is equal to E20 is equal to E30 up to ED0. So the unperturbed energies of these d states are equal, that is d-fold degeneracy. Now, having stated this, I say that okay, I am introducing my perturbation the way I did for the general description of the perturbation theory. So I have this total Hamiltonian, unperturbed part of the Hamiltonian and the perturbation with the perturbation parameter lambda. And what I am interested in obtaining psi n, the final wave function of the perturbed system, En, the final eigenvalue of the perturbed system. Essentially, I want to solve, I want to arrive at this situation, at this solve this problem. Now, suppose I followed this and introduced my perturbation. I had this fourfold degeneracy in this cartoon diagram. I introduced my perturbation and I reached a condition where the degeneracy is lifted because of the perturbation. But if I want to backtrack, if I want to come back by reducing lambda from 1 to 0, I should also be able to get back to my unperturbed state. This is not a problem when I am talking about when I am dealing with non-degenerate states. In other words, when my lambda goes to 0, I should have this wave function psi n smoothly going to psi n 0. This is all right if I am considering a non-degenerate system. But when I have degeneracy in my system, this condition is slightly difficult because I know if there are d number of degenerate states, any linear combination of these states is also an eigenfunction of the Hamiltonian with the same eigenvalue that is for these degenerate states. Suppose I have two states psi 1 and psi 2 which have exactly same energy as E. If I take psi 1 plus psi 2 as a new state, that is also an eigenfunction with eigenvalue E. If I take psi 1 minus psi 2, that also is an eigenfunction with eigenvalue E. If I take psi 1 plus 2 psi 2, then also it is an eigenfunction with the eigenvalue E. So, any linear combination I take is also going to be an eigenfunction of same energy. So, therefore, I cannot guarantee that when I backtrack from the perturbed system to the unperturbed system, that I will reproduce my starting state. I would come back to some combination of these states which corresponds to the same energy, but the wave function will not smoothly converge from perturbed system to unperturbed state. So, that introduces a difficulty. So, in case of degeneracy, what I can say is that I cannot guarantee that psi n would go to psi n 0, but what I can say is that limit lambda goes to 0, the psi n would become some linear combination of this d number of degenerate states. So, psi I 0 is one of these degenerate states going from 1 to d. So, only thing that I can guarantee is that lambda goes to 0, the perturbed wave function will come to some linear combination of this unperturbed state. Now, this is for one value of n. What is n? N is one of these d states. Suppose I have this fourfold degeneracy, I start for this state. When I come back, I can only guarantee that the psi n 0, limit lambda goes to 0, this is some linear combination of these four states. And when I talk about the second state, that means n is 2 now, and I come back to the unperturbed system, then I would get perhaps another linear combination of these four states. So, this linear combination coefficients C1, C2 until CD will keep changing for every value of n. So, that means after perturbation, when I split remove the degeneracy and then backtrack, I would get different linear combination for this starting function. So, that means what? When I am dealing with degenerate perturbation theory, I have another problem to fix, that is to define a unique starting point, and that I say that instead of calling it psi n 0, I am telling that when I remove the perturbation, I come back to this phi n 0, which is simply some linear combination of these I zeros. The coefficients of this linear combination Ci are something that I do not know. I would first like to obtain them, but we will see how we can obtain them and also go ahead with perturbation theory. So, this is my 0th order function, starting function. So, in degenerate perturbation theory, I got another problem that I must prepare my starting function in a particular way, and that way is defined by these coefficients, and these coefficients we will see would be determined will be obtained by defining the form of this perturbation part of the Hamiltonian. Okay. So, in other words, what I am telling is that after doing this discussion, I see that my total wave function psi n after doing perturbation is the unperturbed state. So, please mark here, it is not psi n 0, rather it is phi n0. What is phi n0? This is some linear combination of the psi I zeros plus the usual terms, the first order correction, the second order correction and so on, and the energy terms does not change because any linear combination of these d number of states would give me d number of degenerate states would also give me another eigenfunction with the eigenvalue of same En0. Now I have the definition of psi n and En. I would simply put that in the final Schrodinger equation. So I have H psi equals E psi, and just like the previous case, I would extract terms of different terms of different order of lambda. For example, if I am collecting all the terms which are independent of lambda from this equation, I would see H0 phi n0 equals En0 phi n0. So this is mere statement of the fact that unperturbed eigenvalues and unperturbed eigenfunctions are known, that is lambda 0. This, when I collect the terms with lambda to the power 1, I would see H0 multiplied by psi n1, that is first term, H prime, the perturbation multiplied with H prime with phi n0. These are the two terms in the left hand side. When I look at the right hand side, I have En0 with psi n1, En1 with phi n0. These are the four terms. If you remember, what we did in non-degenerate perturbation theory is to multiply a function to this equation, and we do the same except for one condition, that now I am multiplying psi m0 to this each of these terms from left side and integrating them. So I am multiplying psi m0 complex conjugate and integrating them, and then I am getting this line. What is psi m0? In the non-degenerate perturbation theory, we said psi m can be any of these eigenfunction of the unperturbed system. Now here we are telling psi m is not any of this eigenfunction of this unperturbed system, rather one of these d number of degenerate eigenfunctions. So m is one of these degenerate states such that En0, that is En is the state of our interest, En0 is equal to Em0. So psi m is one of these degenerate functions, nothing else. Now when I evaluate this, let us look at the terms. So the first term in the left hand side, here Hamiltonian is there as the operator, is unperturbed Hamiltonian. The bra has psi m0, so I know Hamiltonian is a Hermitian operator, so I can use the Hermitian property of this Hamiltonian operator, use the turnover relation, so that I get psi m0 on the ket, so that Hamiltonian can act on this psi m0. And when this unperturbed Hamiltonian acts on psi m0, I will get Em0 in this first term of the equation. Look at the first term of the right hand side. The right hand side simply has this En0 in the middle. I can bring this out, so I would get psi m0, psi n1 overlap. The first term in the left hand side and the first term in the right hand side would turn out to be equal. That's because psi m and psi n both have same energy, that is En0 or Em0. So therefore the first term of the left hand side and right hand side, they cancel. That leaves me with this term in the left hand side, psi m0, the H prime phi n0, and the term in the second term in the right hand side where energy is in the middle. I will bring that out from the integration, and I get this psi m0 phi n0. Now here, what is phi n0? Just to remind, phi n0 is the linear combination of some linear combination of this unperturbed eigenfunction psi i's. So we will use that condition now. So here in place of phi n0, I am using that condition that phi n0 is the linear combination of one of these psi i0. So psi i0 is one of these degenerate unperturbed eigenfunctions of the system. Now when I look at this, the left hand side and right hand side both have multiple integrals to be evaluated, because the ket of both the sides have now got summation. So I have to evaluate essentially many terms. So I rewrite that, I take the summation side out, and then I see that I have to, for I goes from 1 to d, d is the number of degenerate states in my system. I have this term which is a matrix element of the H prime. So I am calling this H prime mi. M is the m and I both are one of these degenerate eigenfunctions. The second term has En1 and overlap of psi m and psi I. the psi m and psi i's are the degenerate eigenfunction of a Hermitian operator. So, they follow the standard orthonormality. So, therefore, En1 I am calling them delta mi. When m is equal to I, then it is 1, otherwise it is 0, because they are the eigenfunction of the same Hermitian operator. So, they have to be orthonormal to each other. So, now I see that I have got d number of linearly dependent equations. So, I have a secular equation to construct. So, it will be a d by d determinant. I already have seen this kind of equations when I was talking about linear variational principle. Only thing is that here I would have delta mi, so it's either 1 or 0, unlike linear variational principle. In this case, I do not have this overlap matrix elements to worry about. In any way, let us look at the secular equation. So, essentially I have to evaluate this equation. So, when the non-trivial part of the solution would be essentially opening this determinant and finding the values of E. So, if this is a d by d determinant with these many matrix elements, so I have, when I expand it, I would be obtaining an equation of order d, and therefore, the solution of it will give me d number of energy values. For each energy value, so these d number of energy values are essentially the first order energy correction to the degenerate states. So, by plugging in each value of En that I am getting the d number of values, by plugging in each value of energy, I would get a set of coefficients C1, C2 to Cd that satisfies that particular equation. In this case, in this way, I would do it for d number of time. So, therefore, I get d number of eigenvalues and d number of eigenvectors. So, these eigenvectors are the coefficients C1 to Cd. I would use those coefficients to construct the phi n0. Mind you, what is phi n0? Phi n0 is still the unperturbed eigenfunction, but now phi n0 is defined as a linear combination of some of these degenerate states, degenerate eigenfunctions I zeros, but this is not any linear combination, but rather a particular linear combination that comes out of this secular equation. So, therefore, now what I am doing is that I am ensuring that when I switch off my perturbation, my system smoothly comes back to my phi n0, because I am solving this equation together, so that the perturbation, I know how the perturbation takes the energy forward. I also now know how I can come backward and obtain the proper definition of the unperturbed ground, unperturbed state function phi n0. Now, mind you, I have d number of such functions for d pair of degeneracy. So, this would be the exercise that we have to do for any degenerate perturbation theory. Just to remind you, we see that standard perturbation theory, we cannot apply it for a degenerate system. That is because of the two problems. One is when the systems are degenerate, they have same energy, so the energy difference is extremely small. So, therefore, the influence of one of these degenerate pair onto the state of interest would be exceedingly high, would be unreasonably high, and also we cannot use the standard expression of perturbation theory. The second problem that we encountered is that although after removing this perturbation, we do not know where the system would come back to, because when I have d number of degenerate states, any linear combination of it is also an eigenfunction with the same eigenvalue. But using the recipe that we just discussed, essentially solving this d by d d order equation, or this particular secular equation, we can obtain d number of perturbed perturbed energy values, that is the first order energy corrections, because these are all first order energy corrections that would come out, and simultaneously we will also get a proper definition of IN0 or the starting point unperturbed wave function, which will have a particular definition that will be given in terms of these Ci values coming out of from the solution of this equation. Alright. Now what we will do is that we will apply this degenerate perturbation theory to one particular example, and this example is the excited states of helium atom. Now when I consider helium atom, of course I have a central nucleus, there are 2 electrons. When I imagine this system without any perturbation, that means the electron-electron interaction is the term that bothers me, that is why I cannot solve this problem exactly. So my unperturbed system would simply be a system where there is no electron-electron interaction, that as if I have 2 hydrogenic atoms with Z equals +2 because the helium nucleus. Each electron with to be treated separately with the same nucleus. So therefore, as if I have got 2 hydrogenic atoms over there with Z equals 2. In that case, the unperturbed energy of the helium atom is given as this expression from based on the hydrogen atom solution, where Z is the nuclear charge. In this case, it is 2. Minus half is simply it is expressed in atomic units, and 1 over n1 square and 1 over n2 square is simply n1 and n2 are the principal quantum number of electron number 1 and electron number 2. So we are imagining as if there are 2 hydrogen atoms clubbed together to form this helium atom with no inter-electronic interactions. So the inter-electronic interactions will be introduced as a perturbation. So this is the energy. What will be the ground state energy? The ground state of course we will obtain when n1 and n2 both are 1. So you would see that 1 plus 1 2. So this will be simply minus 4 atomic unit. And what happens to the ground state configuration is 1s2. That means both the electrons are present in the 1s orbital. So therefore n is 1, and that's why we got this energy. Now we are in this case concerned about the excited states of helium atom. How would I do obtain excited state of helium atom? Of course, I have got 2 electrons in 1s orbital. I will excite one of these electrons to a higher orbital. When I do this, the next higher orbital, remember unperturbed system, I am considering hydrogenic system. So the next higher orbital is n is 2. But when n is 2, I have got 2s, 2px, 2py and 2pz. Remember, as long as I have hydrogen atom, that means 1 electron is there. There is the energy only depends on the principal quantum number. So 2s, 2p, 2s, 2px, 2py, 2pz for hydrogen atom have same energy. So therefore, when I excite one of these 2 electrons to this n equals 2, it can go to 2s or one of these 3 2p's orbitals, but in either way it would give me the same excited same energy, because in this case the energy simply depends on n1 and n2. What would be the energy of the excited state in this case? When the second electron is either in 2s or 2px, 2py or 2pz, it would be simply 1 over n1 is 1, because the first electron is still, one of the electrons is still in 1s orbital, the other electron is one of the 2, so n2 is 2. So when I solve this, I would get the unperturbed energy of the excited state. You would see that all these 4 configurations would give me same energy. So that means the excited states are degenerate, and this is where we are going to use our degenerate perturbation theory. Now, since I have got this degeneracy, already I know what should I do. I would have to express as a linear combination of these degenerate states. I have to construct this phi n0 as a linear combination of these psi i's, and this is what I would do. So the unperturbed wave function for this excited state, this is how I am going to construct. So for the time I am giving one electron to 1s and then putting the second electron in 2s. So that way I can construct psi 10. So the psi 10 is simply be the product of 1s function with a 2s function. So I am going to use 1s and 2s orbitals of hydrogen atom, because I am imagining the unperturbed system as 2 hydrogen like systems. But I also want to ensure that indistinguishability of the electron is maintained. So therefore, in addition to psi 1 0, I am constructing psi 2 0, where I am simply exchanging the two electrons. So electron 2 goes to 1s and electron 1 goes to 2s, so that the indistinguishability of the electron is maintained. So this configuration 1s1 2s1 in fact gives me two different starting states, just taking care of the electron exchange. Now psi 3 and psi 4 is the next pair, where one electron is in 1s, the other electron is in 2px, and that is psi 3, and psi 4 is when I am interchanging the electron to ensure indistinguishability of the wave function. Similarly, psi 5, psi 6, psi 7, psi 8, they form the other two pairs, when one electron is 1s, the other electron is in 2py and or 2pz. Of course, I can get other excited states when I move an electron, let us say from 1s to 3s or 3p, but they will have different energy, and at the moment I am only interested in this excitation, where this degenerate pair of excited states, where one electron is in 1s, the other one is going to n equals 2. So therefore, to begin with, I have these 8 number of starting function which have in principle same energy. What would I do? I would simply construct this phi n 0 as a linear combination of psi I zeros, and this equation I can write down for n equals 1 to 8, because now I have got 8-fold degeneracy, because I wrote down this 8 wave functions which will have same energy. Now since I have this linear combination of 8 functions, you can see that I have a circular equation which has this form, which goes from 1 1 h prime 1 1 h prime 1 8, all these matrix elements have to be obtained, these energy integrals have to be obtained. So I have to solve this circular equation. Once I solve this, I would get the energies and the coefficients, and the wave the final results will appear. But before that, we would have to spend some time in doing this the evaluation of these energy integrals. The first term that we will consider is this h prime 1 1. So what is here, I just kept the definition of our wave function. H prime 1 1 is simply the energy integral with respect to psi 1 and psi 1, and then the perturbation term. So helium atom, the perturbation is simply the electron repulsion. In this case, psi 1 0 is electron 1 in 1s, electron 2 in 2s. So therefore 1 in 1s orbital, electron 2 in 2s orbital. The stars show complex conjugate, and in the other side, in the ket side, I have 1s1, 2s2, the same function repeated twice. Now you can immediately identify, because you have already seen these expressions in valence bond theory, in molecular orbital theory. So I can rewrite this 1s star 1, 1s1 separately. That's as the electron density corresponding to the electron 1 in 1s orbital. The second term is electron density of corresponding to electron number 2, which is in 2s orbital, and this 1 over r12 operator makes it as if it is a Coulomb integral, the Coulomb interaction between electron 1 and electron 2. So this is my Coulomb integral. And similarly, I can also write down the same thing for h prime 2 2. Now let us consider the off diagonal elements. So h prime 1 2. Please note that we do not have to worry about the overlap integrals, because they are either 1 or 0 in this case. I am looking at only the degenerate pair of functions, so that's why they are orthonormal. Now I am looking at this h prime 1 2, where the bra side has the same function psi 1, the ket side has psi 2. Psi 2 is simply the exchange of the electron compared to psi 1. Now when I look at this term, the left hand side has 1s1, the right hand has electron 1 in 2s orbital. So there is no such classical description like we had in the previous case, Coulomb integral. So what we can say is that this is actually an exchange integral. It's a purely quantum mechanical phenomenon that is appearing over here. So I would have some exchange integral, and I am calling this k 1s 2s, where this is the exchange integral between 1s electron and 2s electron. And in this case, this is the exchange integral between 1s and 2s. Sorry, in this case, J1s 2s is the Coulomb integral between 1s and 2s. Now let us consider another matrix element H prime 1 3, where left hand side or the bra side is psi 1, the ket side is psi 3. What is psi 1 is, you have already seen, 1s1 2s2. The ket side is psi 3, where electron 1 is 1 in 1s, electron 2 is in 2px. Now here, instead of writing dr1 dr2, I have actually expanded it in terms of dx1 dy1 dz1, and similarly for electron 2 coordinates. Now what is the value of this term, this integral? There is one important feature here, is that we were aware of it, that let us talk about a parity operator. The parity operator, when it acts on its eigenfunction f of x, it makes it to parity operator, whenever it acts on a function, it takes it to f of x becomes f of minus x. It simply change the coordinate. The even function and the odd functions are the eigenfunctions of a parity operator. So in this case, if we change x1, y1, z1, x2, y2, z2 all to their negative values, you would see in that case what would happen is that means I am applying this parity operator for with respect to x1, x2, y1, y2, z1, z2. In that case, you would see that 1s function is totally symmetric, because it has got only r dependence. 2s function also is totally symmetric. 1 over r12 is simply distance between the two electrons. So the distance is obtained by obtaining the x2 minus x1 square, y2 minus y1 square, z2 minus z21 square under square root. So therefore this is also symmetric with respect to parity. 1s1 is again symmetric. Only 2px, which is anti-symmetric with respect to x2 coordinate, because we know that 2px orbital has a nodal plane, and because of that, when I do this parity operation, this h prime 1 3 will become negative of itself, and that would say, because in that case it will violate the parity, and this matrix element has to become 0. Similarly, we can show that not only h prime 1 3, rather h prime 1 4, h prime 1 5 and so on will become 0, and also h prime 2 3, 2 4, 2 5. So all these off diagonal elements beyond the second term would become 0. Now we still have many other energy integrals to evaluate and then look at the solution, but all those things will take up in our next class. So in this lecture we discussed about the degenerate perturbation theory. We discussed why we require a different formulation of perturbation theory for degenerate states. We also learned how to approach do a perturbation theory for degenerate states, and we are in the middle of discussing degenerate perturbation theory for the excited states of helium atom. We will continue our helium atom excited state exercise in our next class. Thank you for your attention.